Okay, so if you imagine our setup, and let's look at one length of the cube, sorry. And we have this standing wave, I'm just drawing n equals 1 for simplicity, that's oscillating. And if we drop an electron right here, we know that this electron is going to oscillate in this field. Okay, I'm not going to do an exhaustive derivation here, but I'm going to show the point that we're trying to prove here. Basically, what do we know? We know that the force on this is going to equal the charge. So let's do orange charge Q. The force on Q is Q times the electric field. We've already said the electric field oscillates, so we know that's true. And let's not forget that this is also equal to the mass. Let's just say it's an electron, okay? Mass of an electron times the acceleration on the electron, which is mass times second derivative of the position with time. So there is a relationship here that once again, I'm not going to do it exhaustively, but basically we land on the force on this Q is going to be equal to the negative of some constant alpha times the position. And that's not too hard to see, right? If you had a position that was a cosine omega t, then the second derivative is just going to be negative, or let's make it sine to make our lives a bit easier. It's going to be negative a omega squared sine omega t. So it's pretty obvious that there's a factor of negative omega squared, and then we get x back. So this is not hard to see, and we already know that our force is going to be Q times E, and E in this case is an oscillating function, right? We recall this. Okay, so what does all this mean? Well, there's a very simple derivation we can do here just to show what the equipartition theory shows for this. So if you have f equals negative alpha x, we also know that f is equal to negative the partial of the energy function of the system with respect to x. Given that f is only a function of x, we can also say that E then is going to be the integration, the two minuses cancel out, the integration of alpha x dx. And I'm going to leave out our constant of integration here, but we just get 1/2 alpha x squared. Now, this is not the full energy function, okay? This is where partial derivatives really comes in. This is a partial derivative. This is the potential energy, okay? There is an energy function for the system that's a whole energy function, and it's energy kinetic plus energy potential. Okay, so once again, simple Newtonian system. And remember, we're still in the Newtonian world where we're saying this particle has mass. It's mass, and it's moving up and down, oscillating up and down. Very Newtonian system. The field is an electric field potential, but nonetheless, it's still Newtonian. So we have 1/2 mv squared plus 1/2 alpha x squared. So I'm going to rewrite these in familiar terms, and I'm going to use some integrals that we solved in a previous video that I'm also going to link up top. But I'm just going to call this a1 p1 squared plus, let's call it b1 x1 squared. Now, to find the average energy of this energy function for this, remember it's an electron that's oscillating up and down, and there is a field here. There's a field, and then there's kinetic energy. Okay, so they actually transfer. These two energy forms transfer between each other. Okay, so what are we doing here? We're going to take the integral. So it's going to be, in rough terms, it's the integral of the probability distribution with respect to E times E, and then over your integration variables, over, same thing down here, probability distribution itself over the integration variables. So for our system, these integrals will be, I'm going to come over here on the left to give myself lots of room. But they're going to be the integral, and remember what P is. I'm going to put another link in top showing what P is because we also derived this thing. Sorry, I wrote this out incorrectly. It's just this, right? But P itself is going to be equal to e to the negative epsilon over kt over the integral of e to the negative epsilon over kt with respect to your integration variables. Okay, so sort of back on track here. Our first integral on top, noting that this is our energy function here, this is epsilon, it's going to be, we get a1 p1 squared e to the negative a1 p1 squared over kt dp1, and this is negative infinity to infinity. And then we get another integral that's going to be part of this because the energy function takes account of all the parts of the function. So then we get negative infinity to infinity on e to the negative a1 p1, nope, sorry. Let's do b1 x1 squared over kt dx1. Okay, that's the first part. And then we get plus, and now it's sort of the opposite, right? It's b1 x1 squared e to the negative b1 x1 squared over kt dx1, and then the other part, which is e to the negative a1 p1 squared over xt dp1. Okay, hopefully I haven't made a mistake here. So we have solved these integrals before, and let's not forget our denominator. All right, so there's a big denominator down here, and the denominator is simply, it's going to be e to the negative a1 p1 squared over xt dp1. Okay, negative infinity infinity, and then negative infinity infinity on b1 x1 squared over kt dx1. Okay, so hopefully I haven't made a mistake here. So really quickly, this guy evaluates to root kt pi over a1, and this guy is root kt pi over b1. These ones like this are going to be, and there's a pattern here, it's going to be kt over 2 root kt pi over a1. This one's obviously going to be root kt pi over b1, and I'm sort of running out of room. I'm going to erase this just to really get this done. We have this thing here is going to be kt over 2 root kt, root kt pi over b1, and then root, the red part is root kt pi over a1. Okay, so what we get is a very interesting result. So if you carefully notice all these groups and you do the mathematics, what you get is E equals kt half plus kt half. So we've shown the average energy of this oscillating system is kt. And what we are going to do, and it's a very important step in the process, we're going to show that per mode, there is an average energy of kt. So just to talk on this a little bit more before I clue up, I'm actually going to have to cut this video into two parts, I think. I'm not going to rigorously show how there's kt energy, average energy per mode, but we can reason it pretty well, okay? So if you have a standing wave, that's n equals 1, okay? And then you have a standing wave that's n equals 2. Obviously it looks like this. There's a couple things that are interesting. First of all, standing wave in this configuration, these blips, as we saw in the simulation, they oscillate twice as fast. They oscillate twice as fast. So because they oscillate twice as fast, and remember that Newtonian energy is correlated with speed squared, they oscillate twice as fast. A particle located in these places, you're going to get a factor of 2. So if this is n equals 2, this is n equals 1. So this has an average energy of kt. Oops. an average energy of kT. This has an average energy of 2 kT. And then, of course, there's a pattern. The average energy per mode is then, per mode is kT. Okay, so like I said, this is not rigorous, but this leads into the next few steps of the derivation, which are very important in sort of showing why this result is so erroneous. And it's interesting because it leads us to the correct result for the energy function of the system. And just to briefly scroll up here, we've seen I've talked about energy functions a lot. Okay, in my video series on statistical mechanics and thermodynamics, I talked about energy function. But one thing to note is that for standing waves in a box, we're saying that this energy function is continuous. And what we can deduce from the result of this sort of derivation is that this is not correct. We'll see this much later, but this is wrong. And really, the quantization of energy comes about because of the result of this derivation. Okay, so I'm going to stop this part here, and yeah, we'll continue next time, and we'll sort of continue down this rabbit hole and see where we end up with an energy calculation for this system. So let me know what you think in the comments below, and please like and subscribe, and I will see you next time.